Episode 35, titled 3.2 Apply Functions and Measures, Mathematical, Logical, Date, String Tools, functions are treated as the small building blocks that quietly power most real analysis work.
A report that looks simple on the surface usually hides dozens of tiny transformations that add up to a final metric someone trusts.
When those building blocks are chosen well, the analysis stays consistent, explainable, and easy to validate, even when the dataset grows or the question changes.
When they are chosen poorly, the same data can produce different answers depending on who touched it last, which is how trust erodes without anyone noticing.
The goal is to build an instinct for which function family fits which kind of problem and how to combine them without creating hidden mistakes.
Mathematical functions sit at the core of measurement because totals, ratios, rounding, and scaling are the language of business outcomes. A total is rarely just a raw sum because the analyst often needs to decide what counts, what unit applies, and whether the quantity is additive across time and groups. Ratios can clarify performance, such as conversion rate or defect rate, but they demand careful alignment of numerator and denominator so the arithmetic reflects the same population and time window. Rounding can improve readability, yet it can also hide small but meaningful changes, especially when audiences compare weeks side by side and assume equal precision implies equal certainty. Scaling is also a mathematical decision because transforming cents to dollars or milliseconds to seconds changes interpretation, and that change must remain consistent across every calculation that touches the field. Logical functions are the gatekeepers of categories, labels, and conditions, and they often determine what a metric really means. A simple condition can separate valid records from noise, such as excluding test activity, removing internal accounts, or marking transactions that should not be counted in revenue totals. Logic also turns messy reality into stable groupings, like labeling customers into segments or labeling events into success and failure outcomes that match the business definition. In practice, logical checks become the backbone of quality protections because they can detect impossible states, such as a cancellation occurring before an account exists, or a negative quantity where negatives are not allowed. The key is that logical rules should be explicit and consistent, because hidden logic creates hidden scope changes, and hidden scope changes create disputes that sound like the numbers do not match. Date functions are the foundation for period-based reasoning because almost every analysis needs to answer when in a way that matches how the business runs. Date logic can define weeks, months, quarters, and rolling windows, and those choices affect trends even when the underlying events are identical. Time differences, such as days since sign-up or hours to resolution, often carry more behavioral meaning than raw timestamps, but they also require consistent handling of time zones and clock sources. When analysts forget that different systems may record timestamps differently, a clean time delta can become a misleading number that shifts across day boundaries or appears to change after a data refresh. A disciplined approach treats date functions as meaning-making tools because time is not just a column type, it is how events are interpreted and compared. String functions are the workhorses of cleaning and standardization, especially when keys and categories arrive as text that looks similar but does not match exactly. Trimming whitespace and normalizing casing often remove the first layer of mismatch that breaks joins and fragments categories. Substring extraction, splitting, and pattern-based replacement can turn a compound label into usable parts, such as pulling a region code from a longer identifier or isolating a product family from a description field. Consistent handling of punctuation and special characters matters because two sources can represent the same value differently, and a single stray character can prevent a match that should be obvious. When string logic is applied thoughtfully, It reduces false uniqueness and makes downstream aggregation behave as if the dataset was designed cleanly from the start. Chaining functions is where power and risk meet, because a pipeline of small transformations can either build a reliable metric or amplify a tiny mistake into a large error. A chain might trim a string, convert it into a structured type, apply a condition, and then compute an aggregate. And each step depends on the previous step behaving as intended. The safest habit is to treat each stage as producing an intermediate meaning, not just an intermediate value, so it remains clear what the data represents after that step. When chaining becomes too dense, reviewers cannot tell where a value changed shape or where a filter quietly removed records, which is why errors can survive into production dashboards. Careful chaining keeps the logic legible enough that a second person can explain it back accurately, which is one of the best tests of analytical maturity. Hidden errors often come from null handling, so nulls should be treated explicitly rather than allowed to drift through calculations as if they were ordinary values. A null is not the same as zero, and it is not the same as an empty string. So a measure that ignores that difference can report performance that looks stable while the underlying data completeness collapses. Nulls also interact with logic in surprising ways, because a condition that checks for equality may behave differently when the input is unknown, and that can cause mislabeling or unintended exclusions. In many environments, a null propagates through arithmetic, which can turn a small set of missing inputs into a large set of missing outputs after derived fields are computed. Explicit null treatment is therefore not only about correctness, but also about predictability, because it prevents a few unknowns from becoming widespread ambiguity.
A sales dataset makes these function families easier to see working together because it naturally includes amounts, categories, dates, and identifiers. Imagine a set of transactions with an order amount, a discount field, a purchase timestamp, a customer identifier, and a channel label, where the question is whether a campaign improved performance without inflating returns. Math functions shape the story by turning raw amounts into net revenue and by computing ratios like conversion or return rate, while logical functions label transactions into included and excluded scopes, such as filtering test orders or flagging refunded orders. Date functions define which transactions belong to the campaign window and compute time to purchase or week-over-week comparisons, while string functions standardize channel labels so email, email, and email do not become separate categories.
When these tools work in a coherent chain, the final metric reflects business reality rather than formatting accidents.
Readability matters because formulas and expressions become a shared artifact that must survive handoffs, audits, and future refreshes without turning into folklore. Clear names for intermediate concepts make a huge difference, such as naming a derived value net amount, rather than leaving it as an unnamed expression buried inside a larger calculation. Consistent ordering helps reviewers follow the logic, especially when the same pattern is used repeatedly across measures, because the brain learns where to look for filters, type conversions, and aggregations. Overly clever expressions often fail in maintenance, not because they were wrong on day one, but because they were too hard to modify safely when a definition changed or a new segment was added. A readable calculation is a risk control because it reduces the chance that future edits introduce silent scope drift. Validation should be treated as part of function work, not as a separate cleanup step, because the best time to catch an error is right after the transformation that could have created it. Known cases provide an anchor, such as verifying that a record with a simple, obvious value produces the expected output after rounding, scaling, or categorization. Edge cases provide stress tests, such as unusually large amounts, empty strings, null timestamps, or values with unexpected punctuation that might break parsing or classification. When testing includes both typical and extreme examples, it becomes easier to distinguish real outliers from calculation defects, which is especially important when a measure will drive decisions. This validation habit also strengthens confidence in results, because it creates a short trail of evidence that the logic behaves correctly under conditions that commonly cause mistakes. Time zone and format issues deserve special attention because date logic can fail silently while still producing plausible-looking outputs. A timestamp recorded in local time may be compared to a timestamp recorded in Coordinated Universal Time (UTC) on first mention, and if that difference is ignored, time differences can shift by hours in ways that change which day an event belongs to. Format differences can also create hidden errors, such as month and day swapping in ambiguous dates, which can distort seasonal trends or make duration calculations appear negative. These issues become more dangerous when analysis spans regions, because the same event might be recorded differently across systems and then merged as if time were uniform. Good date handling includes choosing a consistent interpretation standard and verifying that period boundaries behave the same way across the full dataset, not only in a small sample. Double counting is a common measure failure, especially when aggregates are built on top of already aggregated fields without recognizing the grain of the data. A field that represents daily totals should not be summed again across days without understanding whether the totals already include overlaps or whether the dataset repeats totals per category in a way that multiplies the value. The same problem appears when joining a fact table to a dimension table that creates one-to-many expansion, because a single measure can be repeated across multiple rows and then accidentally summed as if each repetition were new. Preventing double counting requires clarity about grain, meaning what one row represents, and about additivity, meaning whether a value can safely be summed across a chosen dimension. When measures respect grain and additivity, totals reconcile cleanly, and that reconciliation is often the simplest proof that the measure is structurally sound. A short function toolkit becomes useful when it is practiced daily as a repeatable mindset rather than memorized as a list of commands. The toolkit begins with a habit of converting raw fields into stable types and stable categories, then applying clear logical rules that define scope and meaning before computing totals and rates. It includes time reasoning that aligns to business periods and uses time differences to reveal behavior, while also treating nulls as meaningful states that must be handled deliberately. It also includes a preference for small, readable steps that can be validated on known and edge cases, because reliability comes from evidence, not from confidence in a long expression. When this toolkit becomes automatic, functions stop feeling like syntax and start feeling like a structured way of thinking about truth preservation in data. The conclusion of episode 35 sets a practical drill for the week by choosing one function family and exercising it until the patterns feel natural under time pressure. The family could be mathematical for rates and rounding discipline, logical for clean categorization and scope control, date for period boundaries and time deltas, or string for standardization that prevents fragmented groups and broken joins. The key is to pair the drill with small validation habits, such as checking a known case and an edge case, so practice reinforces correctness instead of reinforcing speed alone. Over time, drilling one family at a time builds a balanced skill set, because real analysis rarely needs only one family. It needs them to work together without hidden errors. One focused week of practice is enough to make a noticeable difference in both exam confidence and day-to-day analytical reliability. Thanks for listening. For more audio courses, daily newsletters, and more, please visit baremetalcyber.com.